of communications principles. Today we will have an introduction to analog communication systems. I'm Dr. Abdulrahman Al-Qawasmi from Majma'a University. As you know, the Fourier transform for a non-periodic signal g of t can be given through the integral g of f equals the integration from minus infinity to infinity g of t multiplied by the exponential of minus j 2 by ft dt. This transform, which we call Fourier transform, you studied in the course of signals analysis, and of course the inverse Fourier transform to transform the signal from the frequency domain to the time domain is g of t equals the integration from minus infinity to infinity g of f multiplied by the exponential of j 2 by ft df. As you see, this is what we call Fourier transform pair, and we use these equations in order to transform from domain to another domain and vice versa. The Fourier transform notations. The first one here, g of t is in time domain. This means f Fourier transform. The Fourier transform of g of t will give us the g of f, which means the frequency domain of the signal, or g of f in the frequency domain equals the Fourier transform of g of t in time domain. And this is we use for the inverse Fourier transform. G of t in time domain equals, this is the inverse Fourier transform of g of f. Or if we use this as a system, we have, this is the input of the system, g of t. The system performs Fourier transform of the input, and we have the output g of f in the frequency domain. And this is in the opposite way. This is the inverse Fourier transform of g of f to get g of t. So this one from time domain to frequency domain, or from frequency domain to time domain, and the others, they are all have the same meaning, and we do not hear that we can make a transformation from time domain to frequency domain and in the other direction. Let's have an example how to make transformation or Fourier transform for a rectangular pulse. This is the equation of rectangular pulse. G of t equals a rect t over the period t, which means we have a within the interval from minus t over 2 to t over 2, and 0 for the absolute value of t, which is more or equal t over 2. Using the Fourier transform for the rectangular pulse, we used the first equation of the pair or transform pair. We have that the period now is from minus t over 2 to t over 2 as here for the rectangular pulse. A is the function we have constant a all the time within this period, multiplied by exponential minus j2 by ft, which is a part of Fourier transform equation. In this case, we perform the integration and we have a result sine pi ft equal over pi ft, which is we call sinc. Sinc means the sine of the angle over the same angle. So sine pi ft over pi ft means sinc of ft. See, we don't have pi here, but we have pi here. So it is the sinc of ft multiplied, of course, of at as a result of integration. Here we have our rectangular pulse, g of t in time domain from minus t over 2 to t over 2, and we have the amplitude of the pulse equals constant a. And this is the result of Fourier transform g of f. Of course, we took the absolute value, so the sinc here has only positive values. This is the at from the equation. This is 0, 1 over t took from, if we have f and t, this is our ft, and the other, because 1 over t, as you know, it gives us the frequency, and we have 1 over t, 2 over t, 3 over t, 4. Of course, we have another values, but we took the values that they are connected to, they have 0 values of the sinc. Because if you put, for example, for f here, you see it's for frequency, 1 over t, we have 1, and the sinc of 1 will give us 0. The sinc of 1 will give us 0, and so on. We have 0 values at 1 over t, 2 over t, and of course the absolute values of the frequency. So this is a simple example to refresh your mind about how to make a Fourier transform from time domain to frequency domain. This is a second example, but now we are talking about exponential pulse. This is the function of exponential pulse, g of t equals exponential minus at. Of course, you know this. This is the unit impulse function. We use it with the pulse in order to make our values equals 1 for some interval. A is bigger than 0, which means it is a positive value, and because we have a minus here, we will have a decay exponential pulse. It is which is decreases by time, and at 1 over a we have 0.366. If we of course put 1 over a here, we have the exponential here of minus 1, and it will be 0.366. The maximum value, of course, at 0, not the maximum, because we talk about positive values. So for a equals 0, we have exponential 0, and as you know, the exponential 0 equals 1. We take the Fourier transform for the exponential pulse, of course, for decaying exponential pulse, and this is our result, 1 over a plus j2 by f. This is the Fourier transform of the decaying exponential pulse. We do the same for g of t. Now we have exponential a of t. A now is a positive value, so we have an increasing exponential. Why it is from minus infinity? Because we have u of minus t, which means we have a reversed unit function. So after performing using the Fourier transform, we have the result of Fourier transform 1 over a minus j 2 by f. So we look if we have a decaying exponential, we have Fourier transform as shown here. If we have an increasing exponential pulse, this is the Fourier transform as you studied before. Now, this is a table for the main properties of the Fourier transform. As you know, we use the properties of Fourier transform to make Fourier transform more efficient, more easy, and more simple. So the first property is the linearity, as you know, which means if I have an addition or subtraction between any two functions, I can do the Fourier transform for every function separately. If I have time scaling, which means time scaling, I multiply the time by a for stretching, for example, or expanding. This is the effect of the, which means I can make Fourier transform g of t without a and put a directly in the results of Fourier transform, and so on for all other properties. So please give attention for these properties of the Fourier transform, because when will we discuss the modulation types or techniques used in analog communication systems, it will be useful to know these properties that we will use in the future. This is table of the Fourier transform of the main functions or main signals. For example, rectangular pulse. This is the function in time domain. This is in the frequency domain after Fourier transform. This is what we discussed in our previous example. For sync pulse, if you have sync in time domain, it will be rectangular pulse in frequency domain, which is the opposite way of the first signal. If we have impulse delta function delta of t, the Fourier transform equals 1. For the DC, if I have DC1 or A, the Fourier transform of 1 will be delta function of f. This is for the exponential that we studied. For decay exponential pulse, this is the other one, exponential for the absolute time, and this is the Fourier transform. If I have a unit step function, this is the Fourier transform of the unit step function, complex sinusoidal, cosine wave, and sine wave. So for cosine wave and sine wave, we have to give big attention or more attention, because this is an important signals in analog communication systems. As you know, all electromagnetic waves that be transmitted from the transmitter to the receiver uses the cosine and sine, sinusoidal signals in the forms cosine and sine. And should we know that for the cosine we have this Fourier transform as delta function, and for the sine we have the same but the different. We have plus and we have here minus, and we have here j as a complex number. This is the sync lambda we talked about. This to help you what is the equation of the rectangular and the sync pulse. So Fourier transform pairs is very important, and give attention please in order to simplify understanding the future lectures. This is one of the properties of Fourier transform linearity. We used this linearity in this example. Also, we have an exponential, but we have absolute value a now. The exponential a is more or bigger than 0. In this case, we have, as you see, we have two exponentials, increasing and decreasing exponentials, and we have the Fourier transform of the g of t. As you see, this is for what we before discussed, decreasing and is increasing. Just we make a sum of the rational and we have this result 2a over a square plus 2 pi f square, and this is to give attention for a, the absolute value of a, the absolute value of it, which means if it is positive with negative will be positive, it is negative will be positive, and so on. And this is for the unit step functions. So this is g of t, and this is our g of f. This is another property of Fourier transform, frequency shifting modulation. We will talk about modulation and the meaning of modulation in the future. But here, as you see, I have now a rectangular pulse, what we call radio pulse. Why radio pulse? Because this rectangular pulse now is filled by sinusoidal, as you see, multiplying the sinusoidal wave with the rectangular pulse, we call simply modulation. So the modulation is a simple multiplication between two signals. This is rectangular and this is the sinusoidal. The result of multiplication we have here, and now implying the Fourier transform, we have the Fourier transform result g of t, we have g of f. As you see, the result of Fourier transform of radio pulse, we have two sinks. This sink at the central frequency fc, which we call carrier frequency, we'll talk about, or central frequency, we'll discuss in more details in the future. And this is for f of s also. Now let's remember together what is the meaning of the bandwidth. It is a measure of the extent of significant spectral content of a signal in positive frequencies, which means if I have these positive frequencies, this is our bandwidth, y2w. We have, this is the bandwidth of the signal, and after modulation we have double bandwidth. This is also the bandwidth of the signal before modulation. After modulation it will be twice. So in this case we are considering the bandwidth, those frequencies in the positive side. So from 0 to w, which means w minus 0, we have ww. This is the bandwidth of our signal. In this case we have 2w, because now we have a shifted signal because of modulation, or because of modulation, and we have double bandwidth. We will discuss in the future, but this is how to determine the bandwidth, which is for a band limited signal. The bandwidth is well defined, this band limited, because we have zeros from 0 to 0. But in other cases, as you studied before, we will discuss other methods to define or to determine or to calculate even the bandwidth for unlimited or not limited signals, when the bandwidth is not well defined. The definitions of the bandwidth when the signal is not band limited, different definitions exist. First, null, we call null to null bandwidth, or 0 to 0 bandwidth. Null, the frequency at which the spectrum is 0. For example, we have m of f, of course, in the frequency domain. This is our bandwidth from 0 to the first 0, or from here, from 0 to the other 0, which means this one of ways to define the bandwidth. The definition of bandwidth also can be using what we call 3 dB bandwidth. 3 dB bandwidth, if I have, this is the signal in frequency domain of f, this is what we call 3 dB. 3 dB means that you have to take the 1 over the square root of 2, which means 0.707. This is the limit, and make a cross with the frequency domain, and this will be your 3 dB bandwidth. Why 3 dB? Because the logarithm of 1 over the root square root of 2 is equals 3 dB. So 20 log 1 over 2 will be minus 3 dB, and this is 10 with 1 over 2 equals minus 3 dB. So we call this bandwidth 3 dB. So in order to know the bandwidth in this case, it is easy. Make the level of 1 over root square of 2, and you directly by using this line crossing the frequency, you will have your 3 dB. So M of F or S will drop to 0.07 of the peak value. This is the peak value. This is the peak value. So it is important here to know that 0.07 of the peak value. The peak value in our case is normalized equals 1, so it will be 0.77 of the peak, which corresponds to 3 dB difference in the log scale. On the log scale, this is also 3 dB, but in this, as you see, this is we are working only with positive frequencies. We didn't consider the 3 dB in the negative frequency, but because this all are in the positive side, so now our 3 dB contains FC from both sides, which means it is the double of this bandwidth. This is because of process of modulation, the shifting of the original signal in frequency domain as a result of multiplying this signal by higher frequency. Definitions of bandwidth also use root mean square bandwidth. You can use this equation. You have to know this information and perform calculating using this equation. You will have your bandwidth that we call root mean square bandwidth. Now, transmission of signals through linear systems. You studied in signal analysis systems, and you know there are different systems. One of the important systems is the linear time invariant systems that can be given as this in this equation. As you see, this is the input and this is the impulse response, and we will make a convolution between the input and the impulse response. We have y of t, the output. So this is a symbol, this is a convolution between two signals. H of t is the impulse response of the system. Also, we can perform the to have the output in the frequency domain. In this case, as you see, the convolution process will be more simple as multiplication between the input signal in frequency domain multiplied by what we call the transfer function. So now the transfer function, simply it is the Fourier transform of the impulse response. As shown in this system, this is our input signal in time domain. This is our impulse response. If you are in the time domain, as you know, we have to make something we call convolution, and we will have our output. As you know, the convolution process is multi-stages process, and it is difficult. But in frequency domain, you have to convert or to transform x of t from time domain to frequency domain, and the impulse response to be transfer function. Now simply multiply x of f by h of f, you will have or you will get y of f as the output of the system. And now this output, if you need it in time domain, simply make inverse Fourier transform of y of f to get y of t. Filters. What is the meaning of filter? A filter is a frequency selective device that is used to limit the spectrum of a signal to some specified band of frequencies. Of course, if you have a wide range of frequencies and you want to limit these frequencies to have a maximum and minimum, not to allow for other frequencies to interfere with your signal, in this case you need a filter. So filter selects the bandwidth that you need, and of course for every filter there are three main bands that we call the pass band, there is a transition band, and there is a stop band. But as you know, for the ideal filter, there are only two bands, pass band and stop band. So based on the pass band and stop band and the range of frequencies, we can have several types of filters. We have low pass filter, we have high pass filter, we have band pass filter, and we have band stop filter. This is our filter. This is the transfer function of the filter. This is the input, and this is the output. If we talking about low pass filter, in this case, as you know, your filter will pass only low frequencies and will reject high frequencies. In this case, it is in the opposite way. It will pass high frequencies and reject low frequencies. This is will pass limited bandwidth from between two values, and this is will reject all values inside the frequency interval and pass all other frequencies. So the using of the filter based on the system that you are working with, but basically we use the low pass filter in order in the beginning of every system to eliminate any higher frequency than the baseband signal. The high pass filter can be used for other also purposes to eliminate the low frequencies based on the information or message that you use. Band pass filter mainly used for modulated signals that they are shifted with frequency domain, and now these signals have a limited frequency from one limit to other limit of frequency and so on. This is ideal filters, and as I told you before, when we talk about ideal filters, which means we have only two bands. We have stop band, and we have, this is our pass band. This is our pass band, and this is our stop band. The stop band rejected, the pass band passes our frequencies. So this is high band frequency, this low pass filter, high pass filter. This is for band pass. As you see, it passes only band from 2, and the other will be rejected. Of course, we are talking about positive frequency in this case. For band stop, you see it will pass all frequency and reject only the frequencies in the specific band between F1 and F2. This is the ideal low pass filter. This is the transfer function of the ideal low pass filter. This is the impulse response of the ideal low pass filter. In this case, as you see, we have the transfer function of the low pass filter. It will pass frequency from 0 to B. Maybe this is a bandwidth of voice. If your voice, for example, maximum has 4 kilohertz bandwidth, means the frequency that will be passed using the low pass filter from 0 to 4 kilohertz. And this is the impulse response of the filter in time domain, and you see this is the active and in the time domain you will pass see 1 over P, and of course for filters it is more clear using the frequency domain than the time domain, but we have an energy here and other energies in the unused. So this is the impulse response as a sink, and we studied before that the Fourier transform of the sink. It will give us a rectangular pulse in the frequency domain, and the opposite, if we have a rectangular pulse in the time domain using Fourier transform, we have a sink in the frequency domain, and so on. So we use this property sink, and it will give us a rectangular, and you can imagine this is our A ft over A by ft over by ft, and this is our A in the rectangular pulse. Please refer to the previous examples about Fourier transform properties, and you will understand how we found the Fourier transform. pair between the this is what we call transfer function and the impulse response. Practical filters. Now, when we talk about practical filters, which means the real filters, because there is no ideal filters, which contains only stop band and pass band. There are another filters that contain pass band, transition band, and stop band. So it will not be directly from pass band, stop band, as I don't know. To be stop band, it should go through what we call transition band. So in this case, it is not easy to define the band width, because in our previous case, it was easy. It is B0 to B. It is sharp and clear. But now it is not clear. How can I define now the bandwidth? Because it can be go for unlimited value, for minus infinity, for plus infinity. Of course, we are talking about positive frequency in this case, so we can use 3 dB bandwidth as we studied before. And for this is for signal before modulation, and this is signal after modulation, which will be the double. So this is the 3 dB bandwidth. It is a B before bandwidth, and this 2B after modulation, which will be double. And as you see here, this is our 3 dB level, and this is our bandwidth. In this case, we have this is our 3 dB, 1 over the square root of 2, and this is our bandwidth. So in this case, we use the 3 dB bandwidth to define filters for non-real or for practical filters. The gain of the filter can be expressed in dB. This is our gain of the filter, which 20 log H of F dB, as you know. For other filters, for signals now, if we talk about baseband and band pass signals, for you it is very important to know the difference between baseband and band pass signals. In simple way, we can say that the baseband is the signal before modulation, and it comes directly from the source. For example, your voice using the microphone, or the signal come from the camera, or from sensors, or from measuring tools. This is your signal before modulation. The band pass is your signal after modulation, which means you are preparing your signal for a transmission. So baseband signal spectral magnitude is non-zero, only near the origin, near zero. For example, your voice from 300 hertz to 3300 hertz, about 3 kilohertz. It is your 300 hertz. It is near the origin, and maximum FM is 3.3 kilohertz. This is before your modulation. Now, after modulation, the signal baseband we call band pass. So for this signal, you can use low pass filter. It is a baseband signal. But in this case, you have band pass or pass band signal. After modulation, your signal, now this before modulation, is shifted to by FC. Now your bandwidth is doubled, and now your signal is not baseband. It is band pass, and in order to pass this signal, you need band pass filter. So the spectral magnitude is non-zero, only near the vicinity of plus minus FC, where FC should be more greater than 0. You see here. And it is one of the conditions. If you want to multiply your baseband signals with low bandwidth, with low frequencies, with a higher frequency, with a sinusoidal, with a high frequency FC, this frequency should be very high to make such shift in frequency domain, and it is a requirement in the future, you will see, in order to be able to transmit the band pass signal over the antenna. You cannot transmit baseband signal over the antenna, but you have to prepare the signal by modulation, by shifting, to be suitable for transmission using the antenna. So this is what we call baseband signals, and this is what we call band pass signal. This is an example of modulation, what we call amplitude modulation. Amplitude modulation. This is our baseband signal before modulation. In our example, we have a single tone modulating sine wave signal. This is our signal amplitude modulation after modulation, which is S of t. This is S of t. This is M of t before modulation. In order to make a modulation, we need a modulator. What is a modulator? It's simply multiplication between this input with a carrier. As you see, this is our carrier, C of t, and the carrier, of course, has a high frequency than the frequency of the modulating sine wave signal. In other words, if you are talking about baseband signals, or if you are talking about modulating signal or message, you are talking about the same thing, about the signal or your information before modulation. If your signal is modulated, we are talking about passband signal, or modulated signal, we are talking about the signal after modulation. Of course, in every modulator, we will need carrier. This is the function, sinusoidal. What is the carrier? It is simple, a sinusoidal wave signal with high frequency. Thank you very much for your listening, and please do not forget to submit with my channels to see the other lectures in the future. Thank you again.